of the integration that was discussed as the summation of the two sequences. And here we will consider the example of the differentiator, like the S0 is considered as 1 and S1 is considered as -1. Then Yn will be represented as the S0 multiplied by the Xn plus S1 multiplied by Xn minus 1. And Yn is Xn minus Xn minus 1. This is the response of the digital filter in time domain, that is the discrete time domain. And now if we are interested in order to get the transfer function of the system, then naturally we have to apply here the Z transform, and then the left side will become the Yz and right side will become the Xz multiplied by 1 minus Z to power -1, and hence Yz upon the Xz, that is the Sz transfer function of the system, it will become 1 minus Z to power minus after 1. Now if we are interested in order to get the response of the system, then as we have discussed in the previous example, again we have to replace the Z by e to power j omega. Hence we will get the S e to power j omega as equal to 1 minus e power minus j omega. That is, it becomes here that if we consider e to power minus j omega by 2 as a common, then it will become here the multiplied by in parenthesis e to power j omega by 2 minus e to power minus j omega by 2, and this terms becomes here the sinusoidal function. That is the, now that if we divide this one by the 2 and multiply by the 2, then this total terms will become here the sinusoidal function. Hence this will be equal to the 2 sine omega by 2 e to power minus j omega by 2 plus here the j pi by 2 here. Now here the magnitude of this transfer function will be equal to the twice of the magnitude of the sine omega by 2, and here the phase pi omega will be -1 by 2 omega plus pi by 2. Again we will see that it has a linear, the phase response is changing linearly with respect to frequency, hence the linear phase response. Now if we again see here the power of this one, that is the power, how the power will be represented, that is the square of the amplitude, then it becomes the 4 sine square omega by 2. And if we draw a graph between the magnitude that is in power in dB versus frequency here, then we'll find this response here. Now if we see this response, then it is equivalent to the high pass filter. So we can conclude here that if we consider the differences of the two sequences, then that will be equivalent to the differentiator as we consider in the case of the analog filter. That is a high pass filter here. And if we again we can see here that this is a linear phase response. This is a high pass sharp linear phase response filter. That is a graph between the magnitude, that is the 10 log 10 4 sine square omega by 2, and it is represented in dB versus the frequency here. Now if we consider the some example here of the here the say any Hz is given, and the numerator terms is given by these coefficients here. Say Yn is equal to, this is the here the response of any filter that is given in the Xn side and the Yn side, that is the Yn minus 2.1291 Yn minus 1 plus 1.7834 Yn minus 2 minus 0.5435 Yn minus 3 is equal to the 0.0534 Xn minus 0.0009 Xn minus 1 minus 0.00009 Xn minus 2 plus 0.0534 Xn minus 3. This is the difference equation in time domain. And what is the order of this filter or the system? Yes, response please. Third order. Yeah. The maximum difference that is represented, of the maximum delay that is present in the equation, that will be considered as the order of the system. So we rewrite the response, that is the third order. Your name please.
Sir, Akash.
Akash. Good. So here the now we can write the MATLAB code in order to see the frequency response. How the frequency response will be represented, that is the magnitude and the phase, and also we can analyze the pole zero plot of this difference equation. So what is the purpose of this example? Suppose any requirement is given and from that requirement we have derived the mathematical equation. This is the mathematical equation. Now we are interested in order to see the response of the given filter, means what will be the poles, positions of the poles and zeros in order to analyze the stability of the filter, and also to see what will be the frequency response of the filter, whether the magnitude and phase both are in the permissible range or there is some deviation. So for the purpose of these purposes, to analyze the response or the behavior of the system, we will draw here the frequency response and the pole zero plot with the help of the MATLAB. So here the numerator will be defined by the coefficients here, that is the polynomial will be defined here, and similarly we will define the denominator polynomial. Then we will define the range of the frequency, that is 0 to pi, having a gap of the pi by 511 here. Now H is the FIC-Z. What is the meaning of the FIC-Z? The command FIC-Z is used for which purpose? Yes, response please. There are the two commands which we have described in the previous classes. One is the FIC-S and the second one is the FIC-Z. What is the meaning of the FIC-Z?
The frequency response of discrete time systems.
Frequency response of the discrete time system and in Z plane.
Z plane.
Yeah. Yeah. Yours name? Akash?
Yes, sir.
Okay, good. So frequency response in the Z plane will be represented by the FIC-Z. That is the and how this will be described? Initially, we have to utilize the polynomials, numerator and the denominator. So here we will get the FIC-Z, and the range of the frequency will be defined by the W. And in order to get the amplitude response, initially we have to consider the absolute of this H here. And figure 1 will be describe the plot for the magnitude response, and on the Y level we will write the magnitude, on the X level we will write the omega by pi. So here see, this is the figure 1 that describes the amplitude response, that is the magnitude versus here the omega by pi. Omega by pi is written on the x-axis and magnitude is written on the y-axis. The range of the frequency has been considered from 0 to here the 1, that is the here the range omega is omega by pi. So the total range of the omega is 0 to pi. So omega by pi will become the 0 to 1 here. Now phase response, that is the angle of this one, and this will be multiplied by 180 by pi, and that will be described by the figure 2, and we will get a plot between the omega by pi and the PS. On the Y level we will write here the phase in degree, and on the X level we will write omega in omega by pi here. So here we have written on the x-axis omega by pi, and the y-axis we have written the phase that is in degree. In order to see the pole zero plot, we will use the Z plane, and then we will utilize the two polynomials, denominator and the numerator. And here this is the pole zero plot, having the imaginary part and the real part, and that shows the location and positions of the poles and zeros. Now we can also represent the here the ZPK, that is zero, poles and gain, by using the transfer function to Z zeros and pole conversion, that is a TF2ZP, and utilizing the same constant, that the numerator to denominator, and we will get here the from the transfer function we can get here the zeros and poles location and as well as the gain here. Now if we are interested in order to get here the minimum phase filter, this is a linear phase response, and there are the three terms. One is the minimum phase filter, the second one is the maximum phase filter, and the third one is the mixed phase filter. Just try to understand it. Now if we consider an example, that is the H1Z, that is the Z plus 0.4 divided by Z plus 0.3. So what is the meaning of this one? It means poles and zeros both are lying inside the unit circle, and it is a causal stable transfer function with all poles and zeros inside the unit circle, and that will be named as the minimum phase response filter or the minimum phase filter. Here the numerator will be defined by the polynomial 1 and 0.4. Denominator will be defined by the 1 and 0.3. In order to get the pole zero plot, Z plane, numerator and denominator, and we will see here the pole zero plot. Pole zero plot are like all the poles and zeros are lying inside the unit circle. So this type of the filter will be known as the minimum phase filter. The second is, if we consider here the transfer function h1z, say 0.4 z plus 1 divided by z plus 0.5, and we are interested in order to here the see the location and positions of the poles and zeros, then we will find that one here the zero is outside the unit circle and the poles are inside the unit circle here. So a causal stable transfer function with all its poles inside the unit circle and all the zeros outside the unit circle will be named as the maximum phase. See here, in order to be stable, all the poles must be inside the unit circle. So in the first case, poles as well as zeros, all poles and zeros are inside the unit circle, then that type of the filter will be named as the minimum phase filter. If all the poles are inside the unit circle and zeros are outside, all the zeros are outside the unit circle, then that will be known as the maximum phase filter. Similarly, if we consider here this transfer function h1z, say 0.4 z plus 1 multiplied by z plus 0.4 divided by z plus 0.5 and z plus 0.3. And if we see the position and location of the poles and zeros, naturally we have to define the numerator and denominator polynomials. Then we will use the z plane command in order to see the position and locations of the poles and zeros. Then this is the graph here. And what is the graph? Here we will see that here the some poles are inside the unit circle, some zeros are inside the unit circle, and some zeros are outside the unit circle. A causal stable transfer function with all its poles inside the unit circle and with some zeros inside the unit circle and outside the unit circle will be named as the mixed phase. All the poles are inside the unit circle, naturally that will be the causal and stable transfer function. But some zeros are outside the unit circle and some zeros are inside the unit circle, so it will be named as the mixed phase filter. Recording here. Now we consider here the M point moving average filter. We are just trying the different characteristics of the FIR filter. In order to elaborate the each and every characteristics of the FIR filter, we are just trying to cover some properties of the FIR filter through the examples here. So if we consider here the M point moving average FIR filter with an impulse response, say Hn, is 1.1 by M when the length n lies between 0 to m minus 1, otherwise it becomes 0. So impulse response of the filter exists only when the n lies between the 0 and m minus 1. That is, the length of the filter is capital N, 0 to m minus 1, and for that length the Hn impulse response is 1 by m, otherwise it becomes 0. Now if we apply here the Z transformation to the Hz and apply the formula of the Z transformation, then we will get here the Hz by that is equal to the 1 by m, n is equal to 0 to m minus 1, z to the power minus of the n. Now this can also may be written as something like in this manner, that is the 1 minus z to the power minus m divided by m times 1 minus z to the power minus of the 1. That is a series, GP series here. Now it is equal to the z to the power m minus 1 divided by m times z to the power m multiplied by z minus 1. Now what are the observations by the transfer function? The observations are following here. That is, the first is the transfer function has m zeros on the unit circle and they are at the equidistance and located at z is equal to e to power j 2 pi k divided by capital M, and k lies between 0 to m minus 1 here. Now see here, this is the example, and there are m minus 1 poles at z is equal to 0. M minus 1 poles at the z is equal to 0, and a single pole at z is equal to 1. Single pole, that is the z minus 1, at the z is equal to 1. The pole at z is equal to 1 exactly cancels the zeros at z is equal to 1, pole zero cancellation property. The region of convergence is the entire z plane except at z is equal to 0, because if we consider the z is equal to 0, the transfer function becomes cannot be defined for this value. So the region of convergence is entire z plane except at z is equal to 0 here. Now suppose we consider some example here and say h1 is 1 by 5 multiplied by 1, 1, 1, 1, 1, 1. That is how many points are there? That is the 5 points. 5-point moving average filter, FIR filter. So 5 point. And the second one is the 1 by 9 multiplied by 1, 1, 1, 1, 1, 1 up to the here the say this is, these are the total 9. Yeah, 9, 3, 3, 3, 9. So this is a 9-point FIR filter, are the moving average filter. There are the two filters. One is the 5-point moving average filter, and the second one is the 9-point moving average filter. And we are interested in order to get here the amplitude response and the pole zero plots for these filters here. So we will define the B1 and the B2 and say here the A1 is 1 and A2 is also 1 here. Here H1W is defined with the help of the freq_z command, and we have considered here the total 512 points, and then we will consider here the subplot 2 to 1. There will be gap, and 2 to 1, that is the 2 cross 2 and the first figure. Plot between the omega by pi and absolute value of the H1, and then grading. Title transfer function of 5-point moving average filter here, that is this one. Then 2 to 2, that is the 2 cross 2 second figure. This one, second 2 cross 2, that is second figure, this one. And for this one we will write the title pole zero plot of 5-point moving average filter, and here this is pole zero plot for the 5-point moving average filter. We will consider the same function which we have discussed in the previous case, but we are using here the 2 cross 2 matrix, that is the 4 here there will be the 4 figures, and the first one will be described by the 2 to 1. The second one is, that is the pole zero plot for the first transfer function 2 to 2, and here the this one is the 2 to 3, that is the magnitude plot for the 9-point moving average filter, and this is the pole zero plot of 9-point moving average filter, that is the 2 to 2, 4 here. Now if we see, then what are the differences here? What is the observations? As we are here increasing the points 5 to 9, what is happening? The side lobe attenuation decreases, and our objective is to decrease the side lobe attenuation as minimum as possible here. Now if a frequency response is given, then from the frequency transfer function is given, then from the transfer function, in order to get the frequency response, first z will be replaced by e to power j omega. Now we are concluding whatever we have discussed in the examples here. Z will be replaced by e to power j omega, and then we will get here a complex function that will be a function of the e j omega. And in order to get the amplitude frequency response, h e j omega its square will be considered, that is the hz square is considered at z is equal to e to power j omega. Then we will apply here the 10 log 10 mod of the h e j omega square, that is the f omega, and magnitude that is changing with respect to frequency here, and in order to get the phase frequency response, phi e j omega, that is angle associated with the h e j omega here. The frequency response of 4 common ideal filters in the minus pi to pi range. We consider here the total range from minus pi to pi, because if we consider the infinite frequency, then that infinite frequency will be represented by a unit circle, and unit circle considers here the total range of the 2 pi 0 to 2 pi 360, that is the 2 pi, and the total range will be considered as minus pi to pi, because if we have discussed in the previous class that in order to avoid the anti-aliasing effect, there must be a low pass filter at the input side, and the cutoff frequency of that input will be how much, that will be the fs by 2. That is, here if the total value is the 2 pi, then we will consider only the pi here. So during the time of the designing of the filter, in place of considering the minus infinite to finite range of the frequency, we will consider only from minus pi to the pi range of the frequencies here. And these will be described something like in this manner, that in the case of the ideal filter, the cutoff frequency will lie from minus omega c towards the left side and plus omega c towards the right side, and after this one, this is the stop band, and the range will be shown up to the pi towards the right side, minus pi towards the left side. Similarly, we are interested in order to describe the high pass filter, then we will consider here and this is for the ideal high pass filter. Here the y-axis is showing h e j omega, and for the low pass filter we are using the LP. For the high pass we are using the HP. For the band pass BP, and for band stop we are using the BS at subscript. So here for the high pass, the range, the cutoff frequency will be the omega c to pi here. Here the pass band will be the omega c to pi towards the right side, and minus pi to minus omega c towards the left side here. And if we are interested in order to describe the band pass filter in ideal domain or the ideal band pass filter, then for that purpose we will consider the two cutoff frequencies, lower cutoff and upper cutoff frequencies for the pass band, and omega c1 to omega c2, and for that range of the frequency response will be considered as 1, and for other, that is the 0 to omega c1 as well as omega c2 to pi towards the right side will be considered as the 0. Similarly, in the case of the left hand side, minus omega c1 to 0, it will be considered as 0, minus omega c2 to minus omega c1, it will be considered as 1, and from minus pi to minus omega c2, it will be considered 0 here. So here in this graph we are using the blue lines for the pass band, and the yellow will show here the stop band range. Now if we consider here any filter, suppose this is a low pass filter, we are interested in order to design any low pass filter, and the low pass filter is defined as 1 in this range, that is 0 to omega c, that is the mod of the omega. If lies between the 0 and omega c, then its value becomes 1, otherwise it will become 0, that is from. And if we again see the previous case here, that we will find that from 0 to omega c or 0 to minus omega c, in the case of the ideal filter, frequency response is represented as the 1, and from omega c to pi it is 0, and from minus pi to minus omega c it is again 0, and the same has been represented here mathematically, that is this is the mathematical representation of the same graphical representation for the low pass filter. Now if we apply here the inverse Fourier transformation, that is inverse Fourier transformation for the discrete time signal, naturally this will become here the inverse discrete time Fourier transformation, and for that purpose this will become here the 1 upon 2 pi and integration minus omega c to omega c, then whatever is the response, that is equal to 1 in this range, multiplied by e to power j omega n d omega, and we will get here the omega c n multiplied by the pi n for the total range of the n, that is minus infinite to finite. So this is the frequency response of the ideal low pass filter, and during the time of the designing, if we transform this one in the time domain using the discrete time Fourier transformation, inverse discrete time Fourier transformation, that is the IDTFT, then we will get this type of the response. That is the sync response existing from minus infinite to the plus infinite for the value of the n. And this is the HLPN, impulse response of ideal low pass filter. Again repeating, this is the mathematical representation of the ideal low pass filter. This is corresponding graphical representation of ideal low pass filter in frequency domain. And if it is transferred, or we apply here the inverse discrete time Fourier transformation in order to achieve the impulse response in time domain, then mathematically we can represent this one as the omega psi sine omega Cn by pi n for the n minus infinite to plus infinite. That is the sync function, or graphically we can represent this one, that is the frequency here the impulse response of the ideal low pass filter, whose frequency response is given by this one. Now if we again come to this one, then we will find that it exists for the infinite duration, but for the practical purposes it must be the finite. So in order to make it finite, there are the different approximation or the optimization techniques which are used in order to convert the infinite duration impulse response into the finite duration impulse response. And one of the example is the window, for which we have discussed in the previous classes. Now during the time of the approximation of the designing of the filter, here we see, then we will find HLPN is not absolutely summable because it exists for the infinite duration. So it is, since it is not absolutely summable, and the corresponding transfer function is therefore not bounded input, bounded output stable. HLPN is not causal and is of doubly infinite length. So it is anti-causal here, that physically not realizable. The remaining three ideal filters are also characterized by doubly infinite non-causal impulse response and also are not absolutely summable. When we consider the ideal filter and we are interested in order to design them, then these are the problems which are associated with them. That is they will become doubly infinite and they are not causal here, they are not physically realizable. So we will move for the physically realizable filter that can be designed here. Thus the ideal filters with the ideal brick wall frequency responses cannot be realized with finite dimensional LTI filters here. And in order to develop a stable and the realizable filter transfer function, what we have to do, the ideal frequency response specifications are relaxed by including a transition band. The first approximation, what is the first? That we have to include a transition band between the pass band and the stop band. In the previous case, ideal case, we have considered the very sharp cutoff ideal brick wall, and that has to be replaced by a transition band between the pass band and the stop band. This permits the magnitude response to decay slowly from its maximum value in the pass band to the zero value in the stop band here. Now here in the transition band, this is the value that is attenuating towards the zero. This is the range from omega p to omega s. Omega p pass band is frequency, omega s stop band is frequency, and omega s minus omega p becomes the transition band. And this is 0 to omega p, this is the pass band. And in the pass band, the ripples are allowed having a length of the 0 to plus del p or minus del p, having a deviation of the del p towards the positive side or the negative side, or we can say a deviation is allowed in the pass band. Moreover, the magnitude response is allowed to vary by a small amount both in pass band as well as in the stop band. That is, the deviation will take place in the pass band as well as in the stop band. Typical magnitude response specification of the low pass filter is looks like something in this manner. So from the ideal response, that this is the ideal response, ideal low pass response here, we have to derive the practical low pass filters response in the frequency domain, and that will be approximated more or less something in this manner here, having the transition band, deviation in the pass band, and deviation in the stop band. Now, so far we have seen transfer function characterized primarily according to their impulse response length, whether the FIR or the IIR, magnitude spectrum characteristics, low pass filter, high pass filter, band pass filter, and band stop filter. A third classification of the transfer function is with respect to its phase characterization. That is the zero phase, linear phase, generalized linear phase, non-linear phase. And note that both the amplitude change and the phase delay are changing with respect to frequency, so they are the function of the omega. The phase response theta omega is in terms of the radians, but can be expressed in terms of the time. And we have discussed in the previous class that there is a term that is known as the phase delay, and how the phase delay will be derived from the phase response or the phase plot. So in order to get the phase delay, we have to consider minus theta omega 0 divided by omega 0. Theta, that is a function of the omega 0. If that is divided by omega 0, now it is considered as with negative sign, it becomes the phase delay. Now, if if we are interested for the group delay, then in order to derive the group delay, we have to consider minus d by d omega of the theta omega, and that at the value of the omega is equal to omega c, whatever is the delay, that will be named as the group delay. So if we see, then we will find the ideal filter, ideal low pass filter is very huge, and if the phase spectrum is linear, then the phase delay is independent of the frequency, and it is the same constant alpha for all frequencies. Or we can say all frequencies are delayed by alpha seconds, or the equivalently the entire signal is delayed by alpha seconds. Since the entire signal is delayed by a constant amount, there is no distortion. This is the description of this one, group delay. Group delay means there are a range of the frequencies, and for each and every frequency, if the delay is same, then what will happen? Now there will be no changes in the shape, or we can say there is no distortion in the shape, so information remains safe. So this is the linear phase response. But what is the condition? That theta omega must change linearly with respect to omega. If the filter doesn't have linear phase, then different frequency components are delayed by different amounts, and hence distortion will take place. Now we will consider, in the next discussion, we will consider the different properties of the symmetricity of the linear phase response, and there are the two types of the symmetric. One is the symmetric, even symmetry, and the second one is the odd symmetry. Now if we consider the even symmetry, then even symmetric having the here the even length, the first condition. Even here the even length having the anti-symmetry, the second, are odd length, and that is the symmetric here. Even we consider here the symmetric, then we can consider the even length and the odd length, two conditions. Similarly, if we consider the anti-symmetric, then again we can consider the length of the filter even or the odd. So there are how many conditions? There are the four possibilities of the symmetric conditions. We will discuss these 4 types of the responses of the FIR filter when we will consider the designing of the linear phase response filter. Now, filter designing method. During the time of the designing of the filter, we can there are so many methods that can be used using the MATLAB here. The first one is the windowing. In this one, we apply window to truncate inverse Fourier transform to desired brick wall filter here. And for that purpose, we will use the FIR1, FIR2, or the Kaiser order filter functions here. Similarly, multi-band with transition bands, that is the equiripple or the least square approach. And for that purpose, we can use the FIR-LS, FIR-PM, FIR-PM order. And constant least square filter design method minimize squared integral error over the entire frequency range subject to maximum error constants, and the MATLAB functions that will be used are the FIR-CLS and the FIR-CLS1. Arbitrary response design method. In this one, we use the arbitrary responses including non-linear phase and the complex filters, and the MATLAB commands are the CFIR-PM and raised cosine method, that is for the low pass response with smooth sinusoidal transition, and the filter command, MATLAB command is the FIR-R cos COS. These are the commands which will be used in order to design the filter. But I think today time, what is the remaining time?
So time is 12:43.
12:45. So I think it will be not good today to cover these topics. These topics will be covered for the purpose of the designing in the next class. But at present, we can go through one concept which Ms. Hema Madam and Mr. Dev sir always used to discuss in our class for the purpose of the designing of the filter, that is the FDA tool. FDA tool is a dialog box, and in order to design any filter or in order to see the responses or the performance of any type of the design filter, or to see the performance of the different types of the windows, we have to open the FDA tool. So for the purpose of the FDA tool, you have to just write here the FDA tool and then press enter button, and a dialog box will be opened here. Now in FDA tool, what happens? There is no need to write the commands, but it is just a graphical user interface between the user and the machine, and we will get here the dialog box. But in those dialog box, we have to put the values of the pass band edge frequency, stop band edge frequency, and what is the sampling frequency, what are the attenuation in the pass band, what are the attenuation in the stop band, and so there are the 5 parameters, at least 5 parameters are required, and from where we will derive these parameters. Naturally, we will derive these parameters from the given requirements. So in order to design any filter, whether that one is the low pass, high pass, band stop, belonging to the FIR category or the IIR category, first of all we have to derive the pass band edge frequency, stop band edge frequency. See here, this is a dialog box that has been opened in order to interact with the user for the purpose of the design and designing of the filter here. See here in this graphical representation, that is the filter specification, describes the here the description about the filter that has to be designed. That is, what is the pass band edge frequency, what is the stop band edge frequency, what is the attenuation in the pass band, that is named as the maximum attenuation in the pass band, and what is the attenuation in the stop band, that is the minimum attenuation in the stop band, and at the same time the maximum range of the frequency is the fs by 2. So the fifth parameter is the sampling frequency, that is the fs. Now for example, if we consider here, just I'm giving you some glimpses of the designing. So if we are interested in order to design any filter here, say we are interested in order to design any low pass filter, and so for the purpose of the designing of the low pass filter, we have to select the low pass filter, and then it will be selected in the response type here. Then we will select here the what is the design method. Design method means whether we are interested for the Butterworth or the Chebyshev 1, Chebyshev 2, elliptic, maximally flat, least square, and these will depend upon the type of the filter, because we are searching these in the IIR filter. Similarly, if we search in the FIR filter, then there are the different methods which we have discussed. That is the equiripple, least squares, window, constraints, least square, complex equiripple, maximally flat, least pair, constraint equiripple, generalized equiripple, constraint band equiripple, and interpolated FIR filter. Suppose we have selected here the equiripple, that is the ripples are equal in the pass band, as well as means all ripples are equal in the pass band or the stop band here. Then during the time of the selection of the order, we can specify order from the requirement. If we have calculated the order, then we have can specify, or we can design our filter for the minimum order in order to minimize the cost and in order to minimize the area on the silicon wafer or the memory space. And density factor suppose is given by default 20 here. Then we have to describe here the ranges of the frequency. What is the sampling frequency? By default it has been given 48,000, and pass band frequency 9,600, stop band frequency 12 kilohertz, and say attenuation in the pass band is 1 dB and attenuation in the stop band is 80 dB. So these are the parameters which we have selected here, but these are not just the by trial method, but they have to be derived from our given requirement. So first we have to derive these parameters, these values. Then these parameters will be given as input to this dialog box, and then we will select here the design filter. And when we design the filter, now what is happening, using that method which we have selected here, for example the equiripple, using that type of the approximation, now your system, your computer, with the use of this MATLAB, is trying to design the filter so that we can analyze the performance of that design filter. Yes, see, after designing, we can analyze our filter, means what will be the amplitude response, what will be the phase response, and see here, this is the amplitude response, that is the magnitude response given in dB with respect to frequency. And here we can analyze, that is the analysis, magnitude response is given. Similarly, if we are interested to see the phase response, then we can see here what will be the phase response. And again, if we are interested in order to magnitude and phase both, then we can select this one in order to see the comparison between the amplitude and phase response are both at the same time. What is the group delay for this filter? Naturally, that is constant here. What is the phase delay? That is also here represented in the for the linear phase response FIR filter. What is the impulse response of the filter? Now see here the current filter information, the filter which has been designed. It is the direct form FIR filter, and the order is the 50, and it is stable. The source is designed from the MATLAB here. This is the impulse response of the filter, and impulse response of the filter is given is shown here. And similarly, we can analyze here the step response. What is the step response? Now see this step response of your design filter, and we can also see here the what will be the pole zero plot for that design filter. So here we are using the different types of filter. Okay, what are the filter coefficients? 50 filter coefficients will be represented here. These are the different filter coefficients which are represented here. And we can also see here what is the filter information that is that have been designed. The filter structure is the direct form FIR filter. Filter length is 51. That is the order is the 50, but the length is the 51, starting from the 0. That is stable, yes. Linear phase, yes. Type 1. And the implementation cost will be decided on the basis of the number of the multipliers, adders, and number of the states, and multiplication per input sample and the additions per input sample here. And we can also analyze here the magnitude response estimation and the round of noise in addition of these analysis here. So these are the different types of the analysis that can be done after designing the filter. So we have discussed here what is the method of the designing of the any filter, FIR filter, using here this FDA tool, and after designing we can analyze them. And in the next lecture, naturally we will discuss some more concept, or we will try to elaborate here the concepts of the designing of the FIR filter using the FDA tool. So this is all about the today's class, and thank you very much for patience hearing. And I think there must be some queries after this class, so please go through these queries and please ask the question.